All right, it's 4 o'clock already, so let's start our seminar today. And welcome back to another seminar. So today we're very happy to invite Dr. Liaofan from CIRA. Have anyone know what CIRA is? Yeah, I know some of you might not be familiar with the institution. So CIRA, the full name is Cooperative Institute for Research in the Atmosphere, so which is under CSU. It's like a cooperative institution between NOAA and also CSU. So Dr. Lin, he's the research scientist now at CIRA. So he's originally from Taiwan. He graduated from National Taiwan University for his undergrad, and then he moved to the US, got his both master's and PhDs from Georgia Tech in Atlanta. And then after that, he did 2 years postdoc at University of Utah. And then he moved to Colorado as a research scientist at NOAA. So his research mainly focuses on like the data assimilation application, especially for numerical simulation for weather prediction. So I don't want to spend too much time to, just introduce his excellent background. So now let's give a big hand for him and welcome.
Okay. Thank you for introduction. And my name is Liaofan Lin, and I'm happy to present my research today. And one fun fact in the beginning. So I've been employed by CSU for 7 years. This is my first time entering the main campus. So just let you know. And so today I will be presenting the topics advancing data simulations for rapid flash forecast systems. I want to mention this is a team effort, and so there are big teams working on different agencies contributing to this work and relevant work for the rapid flash forecast systems. I mean, including the collaborators and team at GSL, Global Systems Laboratory, series, CIRA, and EMC, and JSDA. So just want to mention this is a big effort from the teamwork. Okay, so in today's presentation, this is the outline for presentation. First, I will provide a brief overview of data assimilation and numerical weather prediction, NWP. And then I'll introduce the data assimilation framework in Rufus. We call it Rufus. And then I'll present a couple of selected Rufus topics focusing on the observation data assimilation. And lastly, I will introduce a few additional Rufus topics with a focus on cycling strategy and machine learning downscaling. So to begin with, I want to briefly introduce the pathway, why data assimilation is important and how we use it and relevant to our daily life. So I'm using these figures to show how this kind of from the observation and then from the DA data assimilation system to numerical weather prediction to what you get from your phone, the app in your phone. So you can see initially from the observation here, we have all kinds of environmental we have all kinds of observation, including satellite and all kinds of remote sensing observations. We have weather radar, we have surface observations, and we have aircraft, and we have ocean observations, all kinds of data. And in the second chart, you can see we have DA, data assimilation. So basically for DA, it's used to combine observations with prior numerical weather prediction forecasts, and then to produce atmospheric analysis. And at high resolution, we produce at hourly resolutions. And in the third diagram, you can see it's an example of an NWP numerical weather predictions at high resolutions. So currently in operations with HRRR, which stands for high resolution rapid refreshed, and it's operational in the US at 3 kilometers convective allowing the NWP models. And basically it's used the initial condition or analysis from the previous DA analysis and run hourly at NOAA supercomputings to produce those data and we put it in all kinds of sources like cloud or different machines, and then allows private sectors to get it and to do some other processing, which you can see at the last part. For the private sectors, they may do model blendings, they may do bias corrections, post processes, and also interpolate those data for specific location, and then that's eventually how do you get what you get from your apps or from different apps. And next, I am going to introduce the NWP, the concept of NWP. So for numerical weather predictions, we use all kinds of governing physical equations and to solve the fluid dynamics on a rotating sphere. So basically the Earth. And for the model, we discretize the entire Earth. For the global model, we discretize in space and then integrate it forward in time. And in the model process, there are all kinds of procedures for moistures, and there's a phase change. And whenever there's a phase change, it could be produce precipitation, and precipitation could further interact with the land surface. And then there are all kinds of other variables like aerosols can affect with a cloud and radiation. And most common NWP variables, including, let me use the mouse quickly. So most common atmospheric states, including the wind, humidity, temperature, pressure, etc. So show at the it's bottom right. And next, I am going to introduce the short range numerical weather predictions, because there are short range, there are medium range, like from up to 15 days. There's a seasonal or sub-seasonal. So for this study, we focus on the short range. So typically up to 2 to 3 days. And so because the operational weather forecasting is used and maintained and produced by National Weather Service and used by several other government agencies. So it needs to feed some strict timelines and requirement. And currently there are a couple of operational model. For example, for her here, it's running at a 3 kilometer resolution, and it's currently version 4. And you can see there for her there are Conan's domain and there's Alaska domain, and besides there is rapid flash run at a 13 kilometer resolution. Typically, it's focused on from 0 hour to 2 days forecast. And for her specifically, it runs at 3 kilometer resolve allowing resolution. And currently, we are working on the next generations of short range weather forecast system, which we call it rapid flashed forecast systems, RFS. Okay. So next, I'm going to briefly introduce the concept of data submission. So the goal of the DA is to connect the observations with NWP to produce the best estimate for the atmospheric states. So here I'm using some diagram here to introduce how it's produced. So imagine that now we are at the current time, and we will always get the all kinds of observations I mentioned before. It could be radar, satellite, or conventional observations. And at the same time, we got the backgrounds or models or prior forecast from the previous NW forecast denoted as XB. And with the DA, it's kind of statistical procedures to produce XA, or we call it analysis. You can see here, analysis. And then we use that analysis as the initial condition for the NWP to do the forecast for the next hour, as how it's done. And on the right, I am using the most common equation to show how it's calculated. So basically, the analysis is equal to the background plus kind of correction term. And the correction term, there are several components, including the D, and D represent the difference between the observations and the simulated model conditions and model space and observation space. And besides, there are a couple of different covariants that represent the weight, either from the model or from the observation. From the model, we call it B. There's a background error covariance as B, and we have the observation error covariance represent the observation uncertainty. So this is a general concept of data simulation. And next, I'm going to use simple examples using the temperature at one point to explain how this question looks like. But in the three-dimensional, it's certainly more complex. And let's say now we have the model forecast as 20 degrees Celsius XB, and with uncertainty B, which is the variance of the model. And at the same time, we have the real observation, 25 degrees Celsius, and then with the uncertainty, which here I assume as a 1, Rx to 1. And with that, we can use the equation to show at the top to calculate the innovation D, which is 5 degrees, the difference between the Y and 25 and 20, and then comma again here is approximately, you can see of 0.8. And with that, we can get the analysis, which is 24 degrees Celsius. And then I'm using these figures to show how we represent. So you can see this blue curve indicate the model estimate with the best estimate as 20 degrees, as well as the uncertainty. While this represents the observation, the best estimate with uncertainty. You can see once we use the equation to get the analysis, it's not all the way pushed to the observation because it's incorporate both the uncertainty information from the model and the observation to get the best estimate. So that's how the data simulation is about. Okay, so after the overview, next I'm going to briefly introduce the data simulation framework in the current Rufus. That's the system we are working on. So first is a quick timeline of the different versions of short-range NWP systems. So first with HRRR 4, it stands for High Resolution Rapid Refresh V4, and it's at 3 kilometer resolutions, and it has been operational since 2020. And so it's using the WRF ARW dynamic core. And so for version 1, Rufus, and it's expected to be operational sometime this year. And it's instead of WRF, it's using FP3 dynamic core and as well as the GSI data simulation system. And it also runs at a 3 kilometer resolution. So on the right, you can see the domain difference. So the green boxes indicate the HRRR domains, while the yellow box indicate the Rufus V1 domain. And the V2 is the system that we are currently actively working on. And instead of FP3, we're going to transition to MPAS dynamic core, as well as using JEDI. And then similar horizontal and vertical grids may be used. Okay, this slide shows the version 1 data simulation framework. And so currently it's using hybrid 3D ensemble EMVAR algorithms with partial cycling and periodically atmospheric reset. And there are components such as soil nudgings and according to the atmospheric analysis increment. And on the right, I am using a table to provide a summary of the observation platforms as well as the data that we assimilate in these systems. So for the regional systems, I can say approximately we use more than 1 million data points per hour in the systems. And you can see in this table, we assimilate conventional observation. Like here is the surface observations, and we also assimilate the sounding. We have a satellite lightning observations, aircraft observations. We also assimilate GOES, satellite observation. GOES stands for geostationary operational environmental satellite. And then we also assimilate various polar orbiter or satellites radiance observations. Okay, so for this slides, I'm using a summary of the active modeling or DA component that's well working within the Rufus V2. As I mentioned, Rufus V1 is about to be implemented or added to the operation. So we are already fully focused on the version 2, which is maybe to be implemented in next 3 or 4 years. But certainly we are currently working on the Rufus V2. And this slide is from Ming Hu, my colleagues, and he presented in the MS 2 months ago. And you can see in this slide, we use the JEDI, joint effort for data assimilation integrations with MPAS for our version 2 data assimilation systems. And there are many directions and the components are working, and then he summarized or grouped them into 3 parts, including the methods, and you can see too many things. So just briefly mention, we have deterministic component with ensemble components. We have a couple land, atmosphere, and ocean components. And in terms of the observations, we have upper air observations. We have surface observations, radar, and the lightning observations, satellite observations, and then cloud and aerosol. So LD and PM2 aerosol observations. And besides, we have our cycling. We need to investigate our cycling strategy to understand how it benefits our system. Okay, so next I am going to select a few topics focusing on the observation data assimilation to introduce some of our work. So as I mentioned, this system is in collaboration with big teams with different agencies. So I cannot present all of the work, but rather just select a couple of work, and particularly for those led by CIRA, CSU. So here I use the red color to highlight some of the relevant component that is led by CIRA colleagues or folks. And the first is the AMV assimilation. So and next is radar, radio wind velocity DA, satellite radiance DA, and aerosol DA. So next, I'm going to pick up a couple of topics and show the relevant progress or components. Okay, so first is the NVDA. So the DA assimilation of atmospheric motions factor. This work is led by Keenan Yuri, CIRA, and he presented in the annual MS meeting 2 months ago. And so this one is the expansion of GOES MV DA in JEDI. So you can see on the left, I show the experiment design. And for this one, he used version 2 prototypes at 12-kilometer resolutions over the North America, and with the retro experiments with approximately a week, and at hourly data assimilation cycling. And there are 5 experiments conducted by this study. The first one is a control. So for this one, we assimilated aircraft observation only, and then to understand the different GOES MV product. So he incrementally to add a different component and to understand the impact. So the second one is adding the long wave infrared MV observations into the system, and next is adding only the deep layered water vapor MV observation and cloud top water vapor MV, and lastly is adding all of the observations, aircraft and plus those 3 types of observations to understand the impact. And besides, in the system, there are a lot of complex quality observation, quality control procedures. And so I kind of just show some of the high level introduction, including you can see there are troposphere and near surface filtering, And there are quality indicator screening, satellite scenery angles, and bound checks, vertical dependence, error specification, and gross share. There are a lot of details. So that's why I don't show detail, rather just show in general what kind of quality control procedures before those observations can be used for by the system. Okay, so in these figures, I am showing examples of the results. As I mentioned, there are 3 types of MV, but I don't have the space or time to show all the results. So instead, I select this one. So this is examples of the vertical profiles for the long wave infrared DA. And so, as I mentioned, this is 1 week, about 1 week retro experiment. And this one is domain average vertical profile over the entire North American domain. And variable is east-westward wind component, and the observation simulated is GOES infrared MV observations. And for the figure from the left to the right, it first shows the observation minus the background in green. And after DA is observation minus the A bias, and middle is in terms of the Roomy square error. The last one is fitting ratio, and for this one is basically to understand whether the DA system works, and in short, we want the OMA, the observation minus analysis, to be smaller or with reduced the Roomy square error compared to the OMB, which is before the DA, and OMA is after DA. As you can see here, you can see the orange line with smaller Roomy square error compared to the retro run without the DA, or before DA. And this is the same. The bias is also slightly reduced. It shows how the JEDI provides effective DA for this case. Okay, next one, I'm going to introduce the radar velocity, the aliasings with convolutional neural network. So for this case, we have radar winds observations, and you can see here I showed a couple equations. So for this radar velocity, there is a Vmax decided by the frequency and the wavelength, so Vmax. And then so for this one, if the true velocity is greater than this limit, Nyquist velocity limit, and in the data, it will be folded or aliased into the interval between the minus Vmax and the plus Vmax. You can see this provides example. So assuming this is the Vmax, and whenever the true observation is here, and because it's greater than the limit, and it will be folded back to this one. So the true velocity is actually can be recovered using this equation: V observed plus 2L times Vmax. So in this kind of study, the goal is to decide, to understand, to determine the L, the number of falls, to recover the V-true, the true velocities. And this study, I forgot to mention, this study is led by Angie Burks. And for this one, the motivation for this part of the study is to accelerate it, the operational 3-steps radar velocities, the aliasing algorithms using machine learning based methods. So traditionally, we have 3 steps to estimate the L, the number of falls. But this time, we want to see if machine learning can be used and in terms of faster and to estimate the number of falls. And in this study, it treats the aliasing as a pixel-wise classification problem, and it's used the alias, the velocity observation with quantum control as predictors, and using the number of falls as a target or reference. And in terms of number of falls, either -2, -1, 0, and 2 and 1. So I don't know. There should be a third picture there, but it's gone. But let me see. Oh, okay, two slides. Okay, so here is examples. So this is the alias observation. So the original observation we get, and given this is showing examples how the data we can perform or after the aliases, and in the original data, and given the training model, we can the aliens is this one, and then with the number of folds estimated. And so basically the machine, we use this machine and we demonstrate the performance is nearly, I think it's very high, nearly 100% compared to the original operational three radar velocities algorithms. And we demonstrate that machine learning can work to help with this observation pre-processing issue. And next one, I am going to introduce the observation impact. As I mentioned in the Rufus V1, we assimilate all kinds of observations to improve the analysis and to further improve the forecast. And for this study, we understand the observation count within the 4 Rufus domain in V1, showing this blue domain. V1, the domains cover the entire North America. And we also compare this with the data within the Hurricane Helene domain. So over 6 days in this black box. So the figure on the left shows the average observation count over approximately 6 days for entire North American domain. And this one shows the observation count within the hurricane domain. And the y-axis shows different satellite sensors from the top to here. And then from the bottom it's the conventional observations. And one thing to mention is there is an order difference between this one and this one. You can see this is 10 to the 5, this is 10 to the 4. So basically this is much smaller than this one because this is over the Hurricane Helene domain. And then I use the table on the right to summarize the difference between the 4 domain and hurricane domain. What stands out is you can see the satellite data, including the microwave and infrared observations. It retains only 3% of the 4 domain volumes. And while the conventional observations, it retains approximately a third of the 4 domain observations. So the next question is, why does the satellite observations drop so substantially over the hurricane domain, as you can see in the black box? So to address these questions, we plot the spatial distributions of different types of observations. In this case, I use the satellite, which is IRC, meetup C example to understand the infrared observations. And the first things you can see is the hurricane domain, which is shown in the pink box, is relatively small compared to the 4 Rufus domain. And we also found that IRC observations are broadly distributed over land and ocean, over entire domain. And similar patterns are found for other infrared instruments. You can see the red color indicate the infrared. So as a result, only a small fraction of the data is captured in that hurricane domain. In contrast, we compare with the conventional temperature observations. And so this one is using the conventional temperature observation as examples. And here, and as you can see, conventional observations are concentrated over land, especially corners. And we also check other conventional types of observation. They also mainly focus on land. And as a result, much larger fractions of conventional observations are captured over the Hurricane Helene domain. Okay. So next, I am going to introduce the ATM S radiance observation impact in prototype Rufus version 2. And this study is led by Keenan, Yuri, and And so for ATMS, it stands for the Advanced Technology Microwave Sounder, and it's currently on board on several platforms or satellite, including Sumi, MPP, NOAA 20, NOAA 21. And in this study, we assimilate the following satellite channels and different channels that provide different types of observations you can see, including some channels with surface sensitivity windows, temperature information, cloud, precipitation, water vapor informations, and besides, they also follow some different quality control procedures. And in these slides, I am just providing an examples how the observation looks like before and after bias correction. So there is a satellite bias corrections procedures that is applied before we can really assimilate or use that observations in the NWP system. So this example shows the channel 9 observation background history. So and for different satellites or platforms. So the red line shows the results, the observation minus the background before the bias correction. And the green line shows after bias corrections. And as you can see, the bias correction procedures in the JEDI works, and after bias corrections, typically the observations is basically with a mean closer to 0 compared to the observations before the bias correction procedures. Okay, next, I am going to introduce the JEDI-based aerosol data assimilation for roofers. And this study is led by Huiying Rou. And so in terms of the motivation, we know that US wildfire has nearly tripled over the past 3 decades, all kinds of wildfire events. And in HRRR, the operational system, we have HRRR smoke operational since 2020. But since wildfire is getting more increased, and we certainly need to improve our capability to better forecast to the wildfire or high impact events. So for that one, in this study, we implemented the JEDI-based aerosol DA component into the roofers version 1. And we conduct the following 4 experiments to understand different aerosol observations with the system. So first one is the control. You can see control is we assimilate only the conventional and other observations, and we added different aerosol observations one by one. So PNDA, we added additional in situ PM2.5 data observations. And for the third one, LDDA, we assimilated the fierce infrared imaging radiometers suite, fierce LD observation, aerosol optical depth observations. And the last one, we combine both PM2.5 and LDDA observations and with this one. And the question here is how do service PM2.5 and satellite LD observations impact jointly and individually? And this shows the results, the verification against the in situ PM2.5 surface observations over the Western US. You can see the region 8 to 10 is here over the Western US. And the figure here shows the verification in terms of the correlation coefficient and root mean squared error and mean bias with 4 different experiments in 4 different colors. And to take away information is we first find the PM2.5 DA provides a strong short-term service improvement. So as you can see, so PM2.5 DA is in the orange, and typically it has smaller mean bias and root mean squared error compared to the control, the blue one. So it demonstrates the improvement of PM2.5 forecast. And in contrast, for LDDA, is over improved the con structure, but is kind of degrade the surface PM2.5 DA. We find that it's likely due to the LDDA observation itself, it does not have the vertical constraint. And as a result, when we performed PM2.5 surface verification, it degrade the forecast. But in this study, we haven't, in today's presentation, I haven't showed the results for different other type of verification. So this is mainly for PM2.5 verification. Okay, for the next, I'm going to show additional topics, land surface cycling and machine learning downscaling. So again, I showed these slides as a summary before, and then I finished some of the select topics for the observation DA. Now I'm going to introduce kind of cycling strategy and besides spatial topics that is related to DA and as well. And first, as we now transitions from the Rufus version 1 to version 2, and we certainly need to understand, how cycling can further enhance our forecast capability. So I know this diagram is very busy, so, but this is how the DS system looks like. So in the version 1, land surface states are continuously cycled. In contrast, the atmospheric state are periodically reset. So in the black line, it shows how the land surface states are continuously cycled. And so version 2, we certainly need to understand, currently we haven't enabled the cycling strategy in version 2, but we want to understand if we enable it, how does the near surface forecast impact looks like. So for that, we conduct 2 month-long experiments. And the first one, we use the default one, which does not include the continuous land surface cycling. And for the other one, we enable the land surface continuous cycling, and we want to understand the difference between those 2 experiments. And besides, both experiments, they have atmospheric states reset every 12 hours. And for these figures, I performed the verification focused on the 2-meter temperature. And for the DA, we assimilated sounding, aircraft, and in-situ observations for these 2 retro experiments. And for these figures, it shows the verification against the surface 2-meter temperature over the corners. First things you can see, after a few days, so without cycling and with cycling, they start to diverge. And then even after a couple of days, it shows a strong diagonal shift between those 2 experiments. You can see the blue line and red line, they certainly have different diagonal shift. And then we certainly in future, we need to further investigate why there are such diagonal patterns. But in short, here we see it's without and with cycling, they certainly are very different. And next is the dew point verification over the average over the corners for entire May. And so in short, you can see with the land surface cycling enabled or active in the blue line, we can see it's further reduced the average domain-based temperature dew points bias. You can see with the blue line, the mean bias is reduced compared to the one without land surface cycling. But indeed, in experiment, we see there are localized peak showing the blue line, and we in the future we need to investigate this as well. And lastly, I'm going to show a spatial downscaling project using UMNet-based CIRA method, and this is led by Alex Scheid. And the goal for this project is to replace a SmartNet tool. This is a tool that we use to provide the background information for the RTMA, real-time mesoscale analysis. And this one, we want to understand if we can use machine learning-based method that is faster, more accurate, and more portable for future models. And this one, we use UNet-based convolutional neural network, and we use the HRRR 1-hour forecast as a predictors, and we use the IRMA as target or reference. IRMA stands for Unified real-time mesoscale analysis. And in the figure in the middle, I'm showing examples of 1 hour and demonstrated how the machine learning methods works. So this is the typical methods we use, which is SmartNet for temperature. And this is the machine learning based method. And we compared it with the reference, the IRMA. And as you can see, the error using the SmartNet is showing here, and the error between the machine learning based model output with the reference IRMA is shown at the rightmost, and certainly with the machine learning based methods, we can further reduce the errors and provide a better estimate for the real-time mesoscale analysis. Okay, so here I'm going to provide a quick summary and the future directions. Again, I bring these diagrams back to provide the concept. And as for now, we are still focusing on the advancing the next generations DA systems for Rufus version 2, including using the MPass JEDI, multi-scale DA, coupled DA over land, ocean, and atmosphere. But at the same time, we see that increasing needs to use machine learning-based methods across different workflow to help with the entire products, and from the observations to DA to post-processing. And overall, in the future visions, we want to provide an integrated and adaptive system that is physical modeling based, but at the same time data driven. Okay. Lastly, I want to mention some opportunities. So there are all kinds of NOAA scholarship or programs that's for student or also for faculty. And here I want to highlight a couple, including the first one is La Panda student internship programs. And there are Hongley's, this is for undergrad, but undergrad scholarship. There are NOAA experimental research and training opportunities. So there are opportunities. So if you're interested, feel free to reach out. And importantly, they welcome applications not only for NWP, numerical weather predictions, or atmospheric science. As NOAA is an Earth science agent, the NOAA accept applications for a broad range of disciplines, including biology, engineering, mathematical, computer science, hydrology, oceanography, and even social science and policy. So they certainly accept a really wide range of applications and fields. At the same time, we certainly welcome all kinds of forms of collaborations. And with our group, we focus on DA machine learning and multi-scale and coupling modeling, as well as all kinds of Earth system and environment applications. And with that, I'm going to stop here and just I leave my email here. So if you're interested for collaborations or opportunity, feel free to reach out. Thank you.
We do have some time for a couple of questions, so feel free to ask that question. Yeah.
I'm wondering if the refresh system can be used to deliver drainage under a disaster scenario, heavy rainfall like we had here a couple of times, 1997 and 2013, a lot of damage. Could this system have forecasted that so we could adapt quicker?
That's a good question. So certainly this is since this is going to be operational and for the field office like National Weather Office, they use all kinds of information, not just Rufus. They use currently it's they also use all kinds of ensemble based, like her ensemble high resolution ensemble focuses. They combine all kinds of information to predict, to understand how likely such extremes precipitation could happen. But indeed, this kind of system, as well as I mentioned, RRFS itself is not just the deterministic run, it also has the ensemble component. And several of those ensemble components will be the future ensemble forecast system that's used for the field office to be used, to better determine or better track those extreme cases. But yes, to answer question, yes, this will be certainly used to better understand the future extremes events like that.
Like all these QA/QC stuff and like one of the slides you had like a summary of like zenith angle correction and things like that. Are these measures that, like, why were they not in place already? And is it more of a, like, we know how to better adjust this data now that they're being implemented now, or was there just not as much focus before on creating like quality assurance and quality control for the data?
So that is probably related to this diagram. So because our group focus is the DA and the NWP, and while the observations are independently produced by other government agencies, private sectors, or even university or something. So when they calculate, they don't know who will be used. So basically, they just they provide observations and they provide the relevant information. For example, satellite has zenith angles, and that is the corresponding attributes to that footprint of observations. And what we get, because we need to base on those attribute information and to determine how to best use that observations for our NWP or DA systems. So this is kind of the relationship and hopefully explain your questions.
I'll go for it.
Sure.
Would you please go back to the slide that you showed with this one is the land cycling off and the on. So if I'm understanding correctly, the figure is showing the bias. So that value is not the absolute like prediction value. It's like a bias compared to the observation.
Yes.
Temperature. That's correct.
This was the dew point. Yes.
So I feel like interesting is because in the x-axis it shows the time. So that means that it kind of captures the cycle every day.
Mm-hmm.
So that means that at some point during the day, maybe at night or during daytime, you have negative bias. And mostly if you turn off the land cycling, it's gonna be negative bias.
Mm.
And then at some point in the day, during the daytime, maybe it's I don't know, it's at time or maybe it's during the daytime, then you somehow show a better prediction because the bias is near zero. So do you have any explanation why it happens? Depends on the temperature of the day.
So great questions. And so this one, the experiment is mainly to understand the difference between the case with and without cycling. But as I mentioned, this is using the V2, and in the V1, we assimilate as many observations as possible, and we have also the soil nudging in place,
Yes.
which means soil analysis. We update the soil analysis, and that is a more complete system in the RRFS V1 or in the HRRR before. For this one, V2, as we are advanced the capability within different fronts like methodology, observations, or even cycling strategy. We haven't fully integrated such capability, like full set of observation DA. We haven't enabled the soil analysis or soil nudging, and instead this one is only a small component to understand the difference between with and without. So like this one, no soil nudging, no full set of observation. This we only assimilate sounding, aircraft, and institute. So like all kinds of other satellite, no, and many others. So and in the operational system, certainly we have there is much smaller bias in the performance, but not shown here. So this one is more experimental for understanding the cases without. And
Probably it's because you are not including all the measurements that we usually put. So that's why it's usually negative. And maybe like during some certain time of the day, the other factors play a better role for a better prediction. So that's why we see usually negative of the.
yes. And then, well, you mentioned we also will plan to test the soil nudging, which is soil analysis for the Rufus version 2, and then we'll expect to improve the bias situation. And in the future, we even plan to incorporate more strongly coupled the land and atmospheric DA component, and to even helps with near surface forecast in the version 2. But again, this the kind of starting point, early stage point for the Rufus version 2 development.
So do you think that once you put more observations data inside, then these two might become like more deviated or maybe closer? Because right now you're just trying a couple.
In the future, we will certainly enable the land surface cycling. So, but because by default, we don't have the cycling yet. So that's why we need to test if we do the cycling and how it looks like. And then we will further advance to the next stage, adding different capability into the Rufus version 2.
So that's probably a known question.
Yeah. Was step by step.
Any other? Yeah.
Can you show the velocity data aliasing figure 2? So
This one, or
yeah,
you want the
no,
concept,
that's
or
one.
Oh.
Yeah, that how does the pixel wise classification work? Is it sort of just looking for a local spike spatially in the data?
So I need to admit, so this study is not performed by me, so I'm trying my best to explain. Okay, is that okay? So for this one, they provide the input data as a like this is a 2D image as an image, and they provide as many images as possible, and at the same time, they provide the number of fold, the estimate as a reference, using the traditional 3 steps algorithms as the true, and and put it into the machine learning system and to train it and see if the output, which is the alias, can be can provide the number of fold as closer to the true. And at the end, I believe with the machine learning method, because this machine learning is quick, once you have the model and then you provide this kind of alias input and apply the machine learning method, they can quickly provide the alias results as well as the number of folds. And in this other, not this slide, in the seminar, but in Andrew Berg's full presentation, they show the results less detection rate like 99.87 or something percent with the machine learning can that accurately predict or estimate the number of folds using machine learning method. And then that's just, I remember the speed of the machine learning is once in the model, apply this and with the model and then quickly get it. And then to replace the original, the alias algorithm, which is slightly slower. And so that's the goal. We want to accelerate the speed, the pre-observation process steps using the machine learning methods. Yeah, because in the real-time application like this operational method, every minute matters because we need to to do the analysis quicker for the next the focus for the next hour and for the real-time events, extreme events, the precipitation forecast, wildfire forecast. So every minute matters.
All right. Any other questions? I'll ask one last fundamental question about data assimilation, because I believe most of our students probably don't have experience on data assimilation. So you showed in like the very beginnings of your slides, you show like there are 2 curves. One, this one. The blue one is predicted by the background, which is from the model. And then you have the observation curve. So based on this equation, somehow you can find like analysis in between this prediction. So I was wondering, like, why can't we just trust the observation, just use the observation predicted value to correct your model for the next steps prediction? Why we need to do this and to find like we're in between these for data survey?
Okay, so good questions. So in the statistical, there is using example, data fitting issues. There's a issue called overfitting. Like for example, let's say you have a lot of scatter dots, and the most common way to estimate the trend of that scatter dots is linear regression.
Yeah.
And let's say you attend that, but certainly you can use much more curve estimate to estimate, but that will create overfitting issues. And that's why we need to consider both uncertainty in the observation and the model to assuming this is the best analysis, incorporate all the uncertainty, because observation itself, it has uncertainty as well. Let's say, let's say if you measure temperature, at this moment, this location, 10 times, it can give you 10 different measurements. Like I say, we measure the forehead temperature and with infrared sensors, and 10 times that can give you 10 different numbers. And that's why we need to account this one to avoid those kind of overfitting. At the same time, balance all the information across the model and observations.
And those variants just give you a confidence of which one will have you have better confidence on their prediction.
Yes, that is the weights from the observation part and from the model part.
Okay, let's thank Dr. Lin again.
Thank you.